Good morning, dear, and welcome to the lecture of Introduction to Machine Learning. I'm Professor Nandi. So this is my ninth lecture. So earlier, what you have seen that we have solved our linear regression model using calculus method and using normal equation. So those were very good because you had a formula, you had simultaneous equation, you solve them, and you crank out the parameter. And once the parameter is there, your predictor is designed, and then you can use it. But what if the number of features are large, quite large enough so that your number of equations become too many? Okay, so maybe it's 1,000, 2,000, 5,000, so like that. So those up to that somehow, because today we have computer, we have good algorithm, and for solving linear simultaneous equation, so you can do that even. But what if the number of features are 100,000, 50,000? Then it is not convenient because somehow you will have to also invert that W matrix, parameter matrix, and that is computationally not friendly, as you have seen, right? So we'll have to have a method which is called iterative method, which we are going to study today. So yes, you are right. The name of the algorithm is very famous algorithm. Name of the algorithm is gradient descent algorithm. It acts as an optimizer. Okay, I have a objective function which is an error function, as you know, and this gradient descent algorithm will work on that error function, try to optimize the error function, and in that process, corresponding to the optimum values, parameter will be uh, crank out, right? And you will design the predictor. Okay, and what you have seen also, and we have done it, that so that my error function is a convex quadratic function, right? And what is that? Let us try to see pictorially. So this is an example of a convex function, right? Say I have uh, two features. I have plotted one feature along this, another feature along this, and say this is my predictor. Okay, so we can see our objective function nature is like this. So you can consider it as a bed sheet tied at the four corners, and the method of optimization works like this. See, suppose you are rolling a ball from here. So what will happen? Ball will trickle down, will come down, roll down, and it will settle at the bottom, right here. If somebody roll the ball from here, it will also come down and settle down here inside, of course. Ball is here, rolling down from here, so it will settle down at the bottom. So anywhere, from anywhere, if you just try to roll down a ball, okay, what you are saying, by the very nature of the structure, it will settle down to a fixed point which is at the bottom. Now, these balls are actually our weight parameters and initial weight parameter, and we will run algorithm. Now you can understand the language, so that the rolling is actually step by step it will come down. Okay, so we have this kind of function in our linear regression model. Oh, that's very great. Okay, so we'll run gradient descent algorithm here to get the optimum value of the function, and corresponding to those optimum value, and optimum function is of uh, what are there in the function? The parameters, right? And corresponding to this optimum value, we'll get the parameter. So that is as simple as this. Also, you see, if it is 2D, like two features, so we can track the how from initial value how the algorithm is actually running and converging at the uh, at the point here which you are not seeing. Here is a point actually. Yeah? So you have contour. These are called contour. So these actually are contour. So by contour plot, we can check how my algorithm is working. We will come to this. Okay. And so if these are my feature x1, x2, and parameters are attached with these features, as you know, whose value we will try to determine running our gradient descent algorithm. There are, of course, another type of functions which are not so good, means non-convex type of function, which we will not encounter in a linear regression model, but somewhere in machine learning you will come across, we will discuss, right? One of the bad thing about the function is, so wherever you can, it has crest and valley. Wherever you start, it can settle down here, 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 and this is called local optima. Okay, so they are optimum here, minimum in this region, but I cannot claim this is a global optimum value. But here I could claim this is a global optimum, right? So here is called local optima. And so that value could be different. Function is one, right? So that value is different if you search in this space, in this region. That could be different if somebody by chance searching this space, right, for W. Okay, so that's a problem actually. These are called my algorithm has trapped in the local optima. Perhaps you have heard this jargon term. That means actually those are local optima, and to come out from there you can do some trick, playing around with some hyperparameter step length, so that you can come out and then see whether global optimum, say minimum, you are reaching here, or global maximum, which is here, you are able to reach or not. So this type of functions are not so good for running gradient descent algorithm because of chance of trapping in the local optima. But we have strategies even to apply gradient descent algorithm in such functions. We will discuss. This is not our discussion today. Let us concentrate on linear regression model algorithm, right? See, we have our error function, right? So JW is 1 by 2 m summation of I equals to 1 to m h parameters by W xji minus yi square. So this is my error function. So each and every term, you know that this is 1 by 2m. Why we put it? Because of our computational convenience. Okay, because we'll determine gradient, and then 2 and 2 will cancel out. You will see afterwards. So for our convenience, we have added this term. This is x suffix j, j equals to 1, 2, 3, means every feature, these are actually features, x0, x1, x2, a. So this is my predictor, okay, which can be written as w0 x0 plus w1 x1 plus w2 x2 if you have j equals to 1, 2, 0, 1, 2, 0, 0, 1, 2, 3 up to n, right? So the range space of Wj equals, it belongs to n plus, in the range of range space n plus 1 dimension, right? So plus 1 is the dimension. In vector form, we can write like this, that you know. So this is my predictor. You understand? Now let us consider just one sample, right? M equals to 1. So now my error function will be like this. Why we are doing that? Because I would like to derive the gradient of this function. Okay, just first for one sample, because there are n number of features. So step by step we'll have to do, and then we will extend it for m number of samples. So we need to calculate this gradient. Okay, same old story, means we'll calculate the gradient, but here I will not be, I have not I do not have the luxury of putting it to 0 and then cranking out some simultaneous equation and solving them to get deterministic value of W. I do not have that luxury. So what I am trying to do, I am trying to formulate an iterative method so that I can do the same kind of thing, right? So for that, I will have to first find an expression for the gradient. Say now I am making some substitution. I do not want to jump any step. So this is equals to S, my substitution. Okay. Now, from here I can write, so S will be equals to uh, this actually is this, and then, okay, S will be equals to this. Now, if I differentiate S with respect to Wj, what it will be? That's little, this is a vector, although it is a vector, don't worry, it's a little um, uh, linear algebra. So this will be same as if you can consider it as W. So it will be xj. And since minus is 0, right? Because this is not the function of a parameter, it's a level, okay? In case of our housing price, so this is the price of the house, actual price of the house. So you know that. Okay. So now from 1 and 3, I can write down that JW is equals to half S square, half S square. So what will be the differentiation, partial differentiation of J with respect to S? It will be half into 2 into S. You see, 2 cancels out and it becomes S. So exactly for that reason, we have imported in the function half, right? And now I need to calculate this. This is equals to partial differentiation of the cost function with respect to S times partial differentiation of substitute parameter S with respect to parameter. And now you put the value. So this value, this is S we have got. So I put the value of S, and this is we have computed here. We have put the value of this, and then you see this is singing. This is extremely important and so simple. So now I put the value of S. S is equals to H parameters by W, X suffix J minus Y times Xj. Okay, so this is very important formula which time and again you will use for running gradient descent algorithm. And somebody may run the algorithm without knowing where from this expression came. It expression came not from the heaven but from this deduction. It's very simple, right? So this is for one sample. Now for m sample, so gradient will be this, okay, summation of I equals to 1 to m, the predictor hw, h parameters by w, xj, uh, um, uh, suffix I minus y sub I, xj, y xi, right? So these I actually are sample. I equal to 1 to m number of sample, and j is actually feature. J equals to um, 0, 1, 2, up to n for n number of features, right? So this is y0, you remember. This is our fictitious feature x0 we attach with our bias x w0, and then we allow our algorithm to determine this as a parameter. Okay, so and since this is a fictitious feature, we take its value as 1. Okay, now that's great. So you have the expression, and now this is the very important gradient descent algorithm, right? Our gradient descent algorithm is this. Now we have formulated this algorithm. How you see? So xj, so iteratively I'll have to figure out w, right? So sorry, wj is this assignment statement. So new wj will be equal to earlier wj minus alpha times 1 by m times gradient of the function with respect to parameter. Now, these two, 1 by m for computational convenience, and alpha actually is called learning rate. This is basically nothing but step length in a iteration, right? So it has a cosmetic or beautiful term, learning rate. We'll discuss what alpha is. Okay. So now just put the value of this as you have deduced it here in this algorithm. So this is my algorithm, very famous algorithm known as gradient descent algorithm. Descent means my function is convex, quadratic, okay, and the structure of the function is like this, so that it will be always coming down, down, descending. Wherever you initial value, wherever you may start your algorithm, it will descend. Okay. Now you see how the algorithm is working. Say my interest is to figure out this optimum W value. How do I do that? I have this function, right? And I am running the gradient of this function, that is this one. If the samples are given, okay, this can always you can run, right? So, and you are initialize uh, randomly selecting W. So this will be a numerical value only. So let us start. Say I have initial W is here. So this is my W initial. Okay, W I initial. Now, what is the gradient at this point? Gradient is a tangent, right? So, and what is the nature of the tangent? You can see it is a acute angle, right? So it will be positive definite. The gradient will be positive definite. Okay. Alpha is a parameter. First of all, you just is constant, right? 0.01 will come back. Okay. Sometimes 0.01, sometimes 0.1, sometimes 0.001, depending on the type of problem you are solving. So that's why it is called also design problem, right? So nobody is there to tell you, okay, take this alpha value, take this name. So you'll have to design. Okay. Anyway, now coming back to our main problem. So we have started our journey from here. So this become positive. So new W value will be, this W will be assigned earlier W value, which you have selected, the initial value, say, minus this constant, okay, something. So this W, something will be deducted from this W, okay. So next time W will be less. Next time of the iteration, W will be further, say it has come down here. This is again, as long as this is acute angle, so this will be again positive. So again, some fresh intermediate W you will get. So slowly, but steadily, even if you have selected W more than your optimum W, it will be attracted to this optimum W by virtue of this algorithm which we have designed, right? Gradient descent algorithm. What if somebody takes initial value, because you can neither see this in actual problem, because it is not so easy that only one parameter is there, right? Then nobody will solve in this way. Just for understanding, I am trying to tell you, it will be not visible, right? So you can easily, somebody can easily select W in this zone. What will happen? So in that case also, say uh, the W initial, okay. So this will be negative. The tangent there will be negative. So this will be negative. So negative and this negative, it becomes positive, okay. So this W will be added some value, okay, by this term, okay. So this will be positive in this case if you select W which is actually less than optimum value. So iteration after iteration, this value, W value, will be attracted, even if this will be attracted towards this W. So that is, so it is a fixed point attractor property. It has, okay, beautiful property. But so in this way you can run algorithm randomly selecting any W value. Now, how to select step length or alpha? Alpha has a very significant role, as I told you, it's a step length. You can call it learning rate. Okay. If you take bigger step length, what will happen? You're very fast. Your computation will be very fast. You will evaluate, your loop will evaluate quickly, okay, and you will very fast move towards the optimum point. But wait a minute. So computation will be less, right? It's good. So take alpha very high. No, because in that case, there is a chance that, say, this is step length from here to here. This big step length you have taken. So next time from here to here, next time from here to here, next time from here to here, next time from here to here. So it may happen that you missed by this, by taking alpha high enough, you can miss it, right? So alpha should be judiciously selected, and that's why it is called also hyperparameter. It is not the model parameter, but it plays a very important role how your model parameter will converge. Okay, so if somebody select alpha judiciously for her problem, then accurately and with optimum time, his algorithm, her algorithm will converge. Otherwise, uh, it will not. Okay, so this is actually the role of alpha or step length. So it has to be neither very high. High learning rate is bad because you may miss while it gives you fast computation. But taking this too small means your algorithm is actually not, the loops are running with a small step length and it's not progressing. Okay, but you will not miss though this one, but your computation will be high. So you will have to look for it. Now, this is one thing about alpha, which we have discussed. Okay, it's very important parameter. Now, one more thing you should know, that how do I know that my algorithm has converged? Because I cannot see what W value is. That's why my suggestion is, and this is normal the practice, you evaluate the function value, you evaluate the gradient of the function, and keep an eye to them, and you are evaluating of course Wj. Once after one iteration you get Wj, you evaluate this function. But this may, again, that's a design issue, right? If the computation is too complex, if you have 1 million feature, right, then computing this may take time, okay, and resource. But anyway, good way is to evaluate this. What you are getting, evaluating this two simultaneously. See, the moments, the one beauty is wherever you start initially, JW value will decrease slowly but steadily. It will decrease. Okay. If alpha is higher, it will decrease at a faster rate. If alpha is smaller, it will decrease at a lower rate. Okay. It is decreasing, and if you can see the rate of decrease, that earlier epoch or iteration, it decreased that much because it is nonlinear decrease, you see, and now it decreased that much, or it decreased earlier, it decreased this much, this much, this one. Now slowly it is value decreasing value very slowly. Then you can infer that perhaps you are reaching to the optimum point, because you see optimum point here, j value here, j value here. So in the neighborhood of optimum w, uh, j will change very little, very little. Okay, so seeing that, you can just get an idea. And also you can see, this means actually you are evaluating this. Okay, it's very simple with sample very quickly. This is a small computation, so gradient you can evaluate and see. Now, if you started your journey from here, slowly the gradient value will change, and at this point, gradient, so tangent will be parallel to this axis, right? So gradient will be negative, and all of a sudden it becomes positive. Okay, huh? So negative, and all of a sudden it becomes zero, and then it becomes positive. So it changes its sign. Change of sign means you have reached to your destination. So what one can do, one can actually design smartly alpha adaptively, right? So initially, when your change of W is bigger, okay, is moving very fast, your the algorithm will be healthy if you select alpha large, okay, comparatively large, okay, zero point 0.1, for example. Uh, then, as soon as you see there is a change of sign, or JW was not decreasing so much, you just, because very carefully you'll have to look here, okay. This is not this virtual look, you cannot physically look. That means you will have to very carefully uh, decrease the value of alpha, so that you should not miss this point, okay. So in this way, it should not go like this, okay. In this way, you can check the help of your gradient descent algorithm, which is very, very important algorithm, right? So similarly, you see there is also gradient ascent algorithm, okay. When it will be there, okay. So if my uh, function j, not in linear regression, but in any other, because engineers solve optimization problem in many other ways, right? So this is my profit function. I have a software business, I am producing software, and uh, I have a function which incorporates man, material, machines, all kind of things, right? So profit function, which may have lots of parameters, W1, W2, W3, and we need to determine this parameter, right? So in that case, my function, I'll have to generate the objective function. My objective function is a profit one. So it should be an maximization problem I'll have to solve, right? I want to adjust parameter in such a way my profit should be maximum. So this is called, you are running a gradient ascent algorithm. So ascent means your um, you are climbing on this curve and your destination is here, right? So this will be your W optimum. So in that case, the gradient descent, again gradient descent algorithm you can run, because this is a again quadratic function, okay, okay, and so it has unique optimum value, okay. So this is a good. Now here the algorithm sign will only change. Wj equals to earlier W assigned earlier Wj plus, you look it down, plus alpha times this. That's the only change. Okay, and so plus. Why? Because you see here also same thing. If you initialize your W from here with this, that is lower, smaller than optimum value, this initial value, then what will happen? This tangent at this point, the gradient, okay, will be acute angle, right? So this will be positive definite. So this is positive, this is positive. So whatever W you have selected here will be added next time with some value, right? And it will slowly but steadily, it will bring, as long as you are in this zone, okay, in this zone, slowly and steadily it will bring towards optimum value. On the contrary, if you select W randomly in this zone, your gradient will be negative, right? This is negative definite. And then this is your W initial. So then due to this negative value, here it is positive. So the next W will be earlier W this, for example, minus some value. So it will be here. So slowly, slowly, but steadily, you will move towards this fixed point. So here also you can see you have a fixed point attractor, okay. So that's all about gradient descent and gradient ascent algorithm. It's very simple, I think. Now you will have to implement it, okay. It's very easy to implement. And you see, since you are learning machine learning, my suggestion will be you should learn Python, because just like in software development, we have language like Java, then .NET, all kind of things are there. Here in machine learning, you should know Python. It's a very nice language, object oriented, and it's very rich language. It has rich libraries, right? You see, very quickly, many people have contributed to generate high. Um, all the functions are there, but definitely for gradient descent algorithm, you are not allowed to take any help of any function. Just using numpy, that means array, you will have to write the code. It's very simple. So this some of the libraries are numpy, SciPy, then scikit-learn, Theano, TensorFlow, Keras, PyTorch, uh, Pandas, beautiful name, eh? Matplotlib. So these are all Python uh, libraries. You can get used to any one of them. They have a community. They are developing Keras or TensorFlow, right? PyTorch. These are very popular. Pandas. So you'll have to, um, after learning Python as a language, you should be knowing how to use the libraries properly, right? So that your project will be done. Okay, so that's the story I wanted to tell you. Very interesting story, very important story, that how you can, and this will be fortunately same throughout all the other tools and techniques when we uh, mm, discuss. Okay, it's very, very important algorithm, simple but elegant one, and it has various variant, right, types, which we will discuss in the next class. For example, simple vanilla gradient descent or simple gradient descent, then stochastic gradient descent when you have large samples like 1 billion. Okay, so stochastic gradient descent algorithm will work, and then mini batch gradient descent algorithms are there. And in deep learning, you will see lots of variations of gradient descent algorithms are there, and which we'll discuss when we discuss those topics. So thank you for your attention. If you have any question, please come to the discussion forum, and please implement using housing price data. I have made it available in the website, and then we have electronic component quality checking data. So any data you can take and run gradient descent algorithm. Uh, so develop the code and do not use any library, so that you will know how to do the experiment, that how many epochs your algorithm converges. Can you do it better? Or what went wrong that your convergence took 1,000 steps, somebody, your friend took 100 step only. So all this can be learned by doing experiment. So thank you, and stay safe. Have a nice day. Bye bye.